Now operating regions of BJT. There are three operating regions in which transistor is operated generally. Here regions: emitter junction, collector junction, and output, sorry, use of this transistor application will write. First operating region is active region. In active region, it is said to be biased in active region if emitter junction is forward biased and collector junction is reverse biased. If this is a transistor, this junction will be emitter junction JE and this junction will be collector junction JC. We'll see the problems in which we'll explain in detail what is active region or how JE is forward biased and JC is reverse biased. Now when used in active region, it can be used for amplification. So when transistor is biased in active region, it can be used as an amplifier. Number 2 is saturation. In saturation, both the junctions are forward biased. Number 3 is cutoff. When used in cutoff, both the junction are reverse biased, and when operated in these two regions, it can be used as a switch. When in saturation, it is on switch. When it is in cutoff, it is off switch. And last, number 4 is reverse active region. In reverse active region, the position is different, opposite to that of active region. Base emitter junction is reverse biased and collector base junction is forward biased. In reverse active region, transistor operates but it cannot be used as an amplifier. Gain is low in this case, cannot be used as an amplifier. An example: find the transistor currents. Here a circuit is given. Now in this circuit we have given these input and output terminals and this load resistance also connected. We want to calculate the transistor currents. The transistor currents, we are asked to calculate the DC transistor currents. So for DC analysis, these capacitors, which are called coupling capacitors, C1 and C2, these capacitor have capacitance, capacitive reactance, that is Xc, which is equal to 1 upon 2 pi F into C. Now for DC, frequency f is equal to 0. If frequency f equal to 0, then Xc equal to 1 by 0 equal to infinite. If Xc equal to infinite, which it means that when frequency of a signal is 0, that is DC signal is applied, these capacitor offers an infinite impedance, that is they act as open circuit for DC signals. If they act as open circuit for DC signals, we will remove the circuit here, and this circuit will be the DC equivalent of a BJT. Now we will perform DC analysis of the transistor. For DC analysis, we have to check whether it is operating in active saturation or cutoff region, then only after that we can calculate the transistor currents for this circuit. Now we will see first how to check the transistor whether it is operating in active saturation or cutoff. First we will by observation, as this is a NPN transistor. In this NPN transistor, this collector will be N region, base will be P region, and this emitter will be N region. From this base emitter loop, it is clear that this battery is keeping this P type region at higher potential with respect to this N type region. Means base is at higher potential with respect to emitter. If a base which is P type is at higher potential with respect to N type, that is emitter, this base emitter junction is forward biased. And if base emitter junction is forward biased, this VBE voltage will be greater than 0. As base emitter junction is forward biased, this transistor can never be in cutoff. We have already seen the operating regions of transistor. If base emitter junction is forward bias, if base emitter junction is forward biased, transistor cannot be or can either be in active or in saturation. Now from observation, it cannot be said that the collector base junction is forward biased or reverse biased, because we have applied a battery VCC to this collector and battery VBB to base. Both are at positive potential, but we don't know that the whether the potential of base is higher or whether the potential of collector is higher. So now we'll start this problem. Some data is given with this transistor, that this transistor is a silicon transistor and beta for this transistor is 100. VB value is given 5 volt, VCC value is given 10 volt, RC is equal to 2 kilo ohms, and this RB equal to 200 kilo ohms. Now we'll start analyzing this circuit. We'll we'll find out whether it is operating in active or saturation. Now base emitter junction is forward biased, so either it is in active or in saturation. The other junction, collector base junction, the voltage across collector base junction, that is VCB. If VCB is greater than 0, which means this if VCB is greater than 0, means collector is at higher potential with respect to base, means N type region is at higher potential with respect to P type region. So now if VCB is greater than 0, then transistor will be in active region, because collector base junction will be reverse biased, because N type region is at a higher potential with respect to P type region. If VCB comes less than 0 volt, then P type region will be at higher potential with respect to N type region and transistor will be in saturation. Now we'll start the example by assume transistor to be operating in saturation, sorry, in active region. Transistor to be operating in active region. Now for transistors we have some data which are to be used in the examples. This is for silicon, this is for germanium. We'll find germanium transistor very rare. VB value for active region. For silicon transistor which is confirmed to be operating in active region, or if we have assumed to be operated in active region, we will take VB value equal to 0.7 volt, and for germanium this value will be equal to 0.2 volts. If transistor is operating in saturation, this value will be 0.8 volt and this value will be 0.3 volts. If transistor is operating in saturation, or we have assumed that it is operating in saturation, then VC value equal to 0.2 volt for silicon and 0.1 volt for germanium. These three values will be useful in the problems. Now here we have assumed that transistor is operating in active region, and we have given this transistor to be silicon transistor, so VB will be equal to 0.7 volt. Now we'll start analyzing this circuit. Now we have assumed the transistor is operating in active region. We have taken this VB equal to 0.7 volt. Now if we mark all the three currents, this will be the base current, this will be the collector current, and this will be the emitter current for this transistor. Now due to this base current there will be a voltage drop with polarity like this, and due to this base current the polarity will be like this. Due to this collector current the polarity will be like this. Now if we apply KVL in this base emitter loop, we get the equation minus 5 volt plus IB into 200 kilo ohms plus 0.7 volt equal to 0. Now IB is equal to 5 minus 0.7 divided by 200 kilo ohms will be equal to, and it is equal to 21.5 microamperes. Now as we have assumed this transistor to be operating in active region, the equation for collector current IC is equal to beta into IB plus 1 plus beta into ICO or ICBO. Now in this circuit for the data is given for the transistor, ICO is not given, and this value ICO is very small as compared to IB, so this factor will be very less as compared to this factor, so we can say that IC is nearly equal to beta into IB. Now remember here that these two equations are valid only for transistor in saturation, in active region. If transistor are operating in saturation, these two equations will not be valid. So now using this equation we can calculate IC is equal to beta, which is given 100 into this IB 21.5 microamperes will be equal to 2.15 milliamperes. Now we know that for a transistor IE is equal to IB plus IC will be equal to 2.15 milliamperes plus 21.5 microamperes. This will come out to be 2.17 milliamperes. Now here we have calculated all the three currents: base current, collector current, and emitter current, but still we have not confirmed that this transistor is operating in active region. So for it to be confirmed to be operating in saturation, we have to calculate this collector to base voltage, and if this voltage comes out to be positive or greater than 0, then this transistor will be in active region. If this voltage is less than 0 volt, then this transistor will be in saturation. This voltage 10 volts. Now we will apply KVL in this loop so that we can calculate this VCB value. There are two ways we can go in this way also, but there are less component in this way. Obviously we will get same answer in both the cases. Now we'll start applying KVL in this loop. We get minus 10 volt plus IC into RC plus VCB plus VBE equal to 0. Now VCB is equal to 10 minus IC into RC minus VBE will be equal to 10 minus IC is equal to 2.17 milliamperes into 2 kilo ohms, sorry, 2.15 milliamperes into 2 kilo ohms minus 0.7 volt equal to 5 volts plus 5 volt. We are getting VCB positive. So as VCB is positive, collector junction is reverse bias. If collector junction is reverse bias, transistor is confirmed to be operating in active region. So the answers for the currents which are required to be calculated is IB equal to 21.5 microamperes, IC is equal to 2.15 milliamperes, and IE equal to 2.17 milliamperes. Now take one more example. Find the transistor currents. Again we have to calculate the transistor currents. Again silicon transistor is given with beta equal to 100. Now by observation we can see that again this transistor has its base emitter junction forward bias. So now we'll start as base emitter junction is forward biased, transistor is either in active or in saturation. It is operating either in active or in saturation. Now assume, again we will assume transistor to be operating in active region. Assume transistor to be operating in active. If transistor is operating in active region, we can assume this value that VB equal to 0.7 volts. If VB equal to 0.7 volt, now we will apply KVL in this loop and we get the equation minus 5 volt plus IB into RP. The current IB will be like this plus 0.7 volt will be equal to 0. So IB will be 5 minus 0.7 divided by RB, which is equal to 5 minus 0.7 divided by 50k. It is 86 microamperes. Now, as transistor is operating in active, we can use this equation IC is equal to beta into IB, which is equal to 100 into 86 microamperes will be equal to 8.6 milliamperes. 8.6 milliamperes. Now, the third current IE can be calculated by adding these two currents IC plus IB, and it comes out to be 8.68 milliamperes. Now the next step is we have to calculate this collector to base voltage VCB. Again we will apply KVL in this loop and we can calculate this voltage. Now when we apply this KVL, we get minus 10 volt plus IC into RC plus VCB plus VBE equal to 0. Now VCB equal to 10 minus IC into RC minus VBE will be equal to 10 minus IC. Just we have calculated 8.6 milliamperes into 2 kilo ohms minus 0.7 volt will be minus 7.9 volts. VCB is coming negative, so as VCB is negative, JC is forward biased. If JC is forward biased, transistor is operating in saturation. So all the values that we have calculated are incorrect. So now we will calculate all the values again for transistor which is operating in saturation. Remember one thing, that now we have confirmed that this transistor is operating in saturation. In saturation we can assume these two values, VB equal to 0.8 volt and VC equal to 0.2 volt for a silicon transistor. Now once we have proved that this transistor is operating in saturation, we cannot use this equation IC is equal to beta into IB. Remember this thing, this equation is not valid for transistor in saturation. Now this voltage VB is equal to 0.8 volt this time. Now we will calculate this base current IB by applying KVL in this base emitter loop. Minus 5 volt plus IB into RB plus 0.7 volt will be equal to 0. So IB will be equal to 5 minus 0.7 divided by RB will be equal to 5 minus 0.7 divided by 5 minus 0.8 volt. VB equal to 0.8 volt for saturation divided by 50 kilo ohms will be equal to 84 microamperes. Now to calculate this collector current, we cannot use this equation IC is equal to beta into IB. It is not valid. To calculate this collector current IC, we already know this collector to emitter voltage VC equal to 0.2 volt. So by applying KVL in this loop, we can calculate this collector current IC. So when we apply this KVL, we get the equation minus 10 volt plus IC into RC plus VC equal to 0. Now IC is equal to 10 minus VCE divided by 10 minus VCE divided by RC. it is 10 minus 0.2 volt divided by RC, which is equal to 2 kilo ohms, and it comes out to be 4.9 milliamperes. Now the third current IE will be, the addition of these two currents will be equal to 4.9 milliamperes plus 84 microamperes, which is equal to 4.98 milliamperes. So these are the three currents